Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture, and in this lecture we will pay our attention to very important testing, fracture toughness testing. Okay, so we'll go through a lot of information in this lecture about this very critical test in the fracture mechanics subject. And what we will now look at is some of the salient features. In comparison to simple tension test, the test to evaluate fracture toughness is more involved and several requirements have to be met. It is not, it cannot be compared to, in fact, any other mechanical test in terms of criticality and the critical analysis are concerned. This is quite involved test. Okay. So the fracture toughness is a function of specimen thickness, and one should use appropriate values of plane stress and plane strain cases. This we have already seen in the previous lecture about this, how the fracture toughness varies with the thickness. In fact, I said this could be the one of the problems, like how to select the thickness for a given material to attain a particular plane strain condition or a plane stress condition, etc. The procedure for plane strain fracture toughness testing is well developed and codes exist to conduct this test. The procedure for plane stress testing is still developing. The toughness value is also a function of panel width. So if you look at these plots of K versus thickness, this is typically for a steel data. K1C is or Kc is a critical stress intensity factor, which varies from the small thickness to the larger thickness. That means plane stress to plane strain condition. That is what it is. And for this aluminum alloy, it is varying like this from plane stress to plane strain condition. And what is interesting to note here is, if you look at the steel data, approximately around 25 mm, the plane strain condition is obtained in the case of steel. On the other hand, only 15 mm of thickness in aluminum alloy, it reaches the plane strain condition. So this is something very different. I mean, that is important to note that every material will have a characteristic thickness of specimen dimension for fracture toughness testing. This is an important point to note. Okay. The other point to notice, fracture toughness is a material property. Fracture toughness becomes material property only when plane strain conditions are met in an experiment. This is all well established now. This imposes a minimum requirement on the specimen thickness. For a new material, it has to be obtained by trial and error. Okay. For the test to be valid, one should do the test with a natural crack. That means you cannot make a notch or a wire cut and so on. It has to be grown by typically a fatigue loading. And special notches are recommended to get the natural crack by fatigue loading. There are notch designs which we will discuss how it is being done in the typical test. And the requirements of the tests are the following: constraints on specimen dimensions, fatigue pre-cracking restrictions, and loading rate recommendations, post-mortem of fatigue pre-crack. Okay. All these above requirements are given in this ASTM code. So it is quite elaborate details are given for this kind of important testing. So candidate fracture toughness. What is candidate fracture toughness? Generally, the value of K1 determined from the test is labeled as KQ, called candidate fracture toughness. So this is a test outcome, and it will be recorded or declared as K1C only after certain conditions. Only when all the requirements of the tests are met, it is accepted as K1C. So this is important. Post-mortem of the experimental parameters is unique to fracture toughness testing. It is very difficult to predict all these parameters before experiments. Once the experiments, after experiments, the parameters are not followed, then the test has to be scrapped. Specimens for fracture toughness test, again, it is need based. Select those specimens for which the accurate analytical expressions exist to evaluate the value of stress intensity factor from experimental parameters. The popular ones are compact tension specimens, known as CT specimen, 3-point bend specimen, TPB specimen, and C specimen, and disc-shaped compact tension specimen. So all this, all also different uses. You can see that CT specimens are useful in the plate stock, and C specimens are useful for pipes, and the disc-shaped compact tension specimen is useful for the round stock. Okay, so the miniature compact tension specimen are used in the special applications where the material availability is critical. Then this kind of specimens are prepared for conducting this fracture toughness test. So what you are seeing here is a compact tension specimen dimensions, and you can see that the values or A by W values are given here with respect to this thing, and this is the typical expression to obtain the stress intensity factor as a function of A by W for this particular geometry, and this expression for K1 is accurate to 0.5% and valid for A by W ratio of 0.2 less than A by W. I mean, A by W value should be within 0.2 to 1. So this is very important to note. And this is the notch we talked about. We will separately discuss how to understand this kind of a notch. Next one is the 3-point bend specimen, and we'll have a separate empirical relation for K1 as a function of A by W, and what is shown here is the dimensions are all shown here. Then you can just understand this. This expression for K1 is accurate to 0.5% in the range, and what is given is S is equal to 4W. You can use that in the formula. C specimen or DCT specimen, useful for the fracture toughness testing of tubes. So it is nicely configured in that manner, and you can look at this kind of an expression for A by W configuration. And the disc-shaped compact tension specimen are also useful for the shafts, testing of shafts. So the expression is different for this dimension. You can see that. So, but all of them are already they are all also given in the ASTM codes. So this is just for a reference. You should know what are all the types of specimens available and why it is given, and so for that reason only I brought all of them. So now let us look at what are the constraints on the specimen dimensions. This expression we have already seen. The minimum thickness of the sample should be B, which should be equal to or greater than 2.5 times K1C by sigma ys to the power 2. Ensures the plane strain condition. For aluminum alloy 15 mm, nuclear grade steel it is 1020 mm. So this is very interesting to note. You know, so finding out the K1C for such kind of thickness is not possible because of the conditions. And ligament size is, the lateral, okay, so the width is should be greater than or equal to 5 times K1C divided by sigma ys to the power 2. Lateral free surface should be away from the crack tip. That is another condition for this. And A should be greater than or equal to 2.5 times K1C by sigma ys to the power 2. And crack is long enough to ensure reasonable load to fracture. So these are all the very strict specimen constraints for fracture toughness testing, and we will just see the approximate thickness required for a valid K1C test. This is for generally steel. It is 690. Okay, it is given in MPA and KSI depending upon this. And if it is of this range, then the thickness is should be 76 mm or greater. Depending upon the sigma YP, that is yield point, these values, then this is also vary. Okay, that's constraint, at least for testing common material like steel and aluminum is given here. And this is just for reference. Okay, now I was just mentioning about this notch. Now we will look at what is the importance of this chevron notch. Chevron notch, the side view is like this, and then the slot width is W by 10, and slot machined to 0.45 W and extended at least by 0.5 W by 50. So this is by it. So to understand this geometry, you should cut this specimen in the plane, this perpendicular to the screen, that plane. And this chevron notch is used to control the origin and plane of the fatigue crack growth. So in this plane, the fatigue crack will grow, and then we will just try to cut this plane like this, and then we will see how it is looking like. So after cutting this plane, the notch, will look like. So the point is, when the specimen is subjected to the loading, tensile loading, and this point will be the weakest, so the crack will initiate from here and then will grow. The crack will grow like this. So this is how, and the crack propagates in the plane, same plane. So that is the advantage of having chevron notch. And in fact, most of the CT specimens will have this kind of chevron notch made. And what are the fatigue pre-cracking restrictions? Excessive plastic deformation near the crack tip to be avoided, and that is a precondition. And maximum stress intensity factor of fatigue loading should be less than 0.6 kQ. That is a candidate fracture toughness value. A high K may blunt the fatigue crack too much, leading to unconservative fracture toughness values. Last 2.5% of the crack growth, crack length should be loaded at a maximum K1 such that KQ by E should be less than 0.32 into 10 to the power minus 3 square root meter. So that is the kind of crack growth condition at the final stage. So this is again shown how the crack grows and then will propagate and originate and propagate further. It's shown here. And some of the experimental procedures use special fixtures to load and the pre-cracked specimen. Loading rate should be maintained in the range of 0.55 to 2.75 megapascal square root meter per second. Record load displacement curve. The transducers are to be selected such that maximum load can be determined within 1% accuracy. The specimen is tested until it can sustain no further increase of load. It is like some simple pulling, but with all the preconditions. And what is to be noted now is how the clip gauges are fixed to measure the CMOD, crack, mouth, opening, displacement. Okay, this is called CMOD, and typical gauge length. The gauge is fixed here, and this is a mounting type, and this is a chevron notch, and this is a close-up view how this gauges are fixed, and what we are trying to. Now we will see how the data is collected, and so load versus displacement. You will have the PQ value. It is the load maximum PQ to be determined better than 1% accuracy, and a smooth COD. That is there's a kink in COD and a smooth COD curve. You will see that then the point of PQ is at 5% tangent line, and line with 95% of the initial slope is 5% secant line. Sorry, not tangent line, secant line. So this is 95% of the initial slope is 5% secant line. So we will see that some of the load versus displacement curve also will have some in between step or a kink, you can call it. Then also, yeah, there is a pop-in phenomenon. So in this case also, you have to take the 5% secant line to take the PQ value. This kind of load displacement data one normally obtains in the medium thickness specimens. One is extreme thin specimen and thick specimen, and in between specimen also you will get the pop-in phenomenon. So once again, this is the KC versus thickness data which you have seen in the previous lecture. So you can see that the plane stress to plane strain as the specimen thickness increases. So this is an intermediate thickness where a pop-in phenomena may occur, but this is a plane strain condition, this is a plane stress condition. Failure of specimen in tension test is, which is normally accompanied by this, cup and cone fracture with a shear lip. So similarly, here also you see that the shear lips are possible because as a crack growth and then catastrophic and sudden failure also will involve this shear failure in fracture toughness test. And the influence of specimen thickness on the nature of specimen, again, nature of specimen failure about this shear lip formation. So this is for the plane stress condition, and then this is a plane strain condition. The plane strain condition, you can see that this is a long crack growth, and then finally the shear lip formation takes place at this kind of setup. So now what we will do is we will look at very important aspect, measurement and acceptance of the criteria for a crack length. So the crack, pre-crack we have generated, and then how to make sure that that is really valid. So what you are seeing in this sketch is this is a crack growth region, and this is done by fatigue pre-cracking, and then this is a fracture surface. This is, you can see that actual specimen where you can see that fatigue crack growth region appears bright as compared to the fracture surface here. So the measurements are made, the crack length measurements are made at the 3 locations, and then some kind of an average is taken here. So A is equal to 1 by 3, A1 plus A2 plus A3. A1 or A2 or A3 should not differ more than 5% of K. So that is a condition. This is a post-mortem analysis. So it has to make KQ as K1C. Then these are all the one of the conditions, pre-crack conditions. Okay. So now sometimes the crack lags behind the shear lip. Test not valid if any part of the crack front is closer to the notch than 0.05 or 1.3 mm, whichever is smaller. Surface crack length should not differ from average length by more than 10%. So this is again another condition which is very strict for this test. So now we understand that these are all very critical and difficult experiments to perform. And how do we select the specimen from the stock? There are some recommendations. Where there is, suppose if you have the material stock of this nature, then how do we take the samples? And so this is a table specification where you have an axis and the crack orientations are given, where L is longitudinal, T is transverse, and S stands for short transverse. So toughness values for ST directions may be 30 to 60% lower than the LT directions. So this is some recommendations about how to prepare the samples or how to take the samples from the material stock before we perform the test. So that is very important. And this is also given in some of the codes, but just to give an idea in a bulk material how to take the samples. So this is just to give you an knowledge about the testing as well. So some of the plane strain fracture toughness values for the selected engineering alloys, what you are going to shown here, just to give an idea about what kind of material we are dealing with. 4340, it's all very important steel, which is after tempering at 260 degrees centigrade, that is quench and temper condition. This is a yield strength value, and then you have 15 to 63 MPa square root meter, and you can see that other type of grades, very heavily alloyed steels, you can see that they all have very high fracture toughness. Okay. And then you also have maraging steel, very important steels. You can see the strength values are extremely high, and then still they are able to have very high fracture toughness because of the alloy design and heat treatment and so on. This is for non-ferrous alloys, aluminium, and you can see that strength levels are very different from the steel, and then the K1C value is also accordingly very different as compared to steel structures. Just give you a perspective about what kind of values one expect in an engineering alloys. Okay. So this is for same material with the different grades. And then all this aluminum alloys are typically again subjected to different heat treatments, and just not given because quite elaborate treatment. So the T, when you say T, this kind of a coding will also indicate the type of heat treatment the materials subjected to. For titanium alloy, this is Ti64, titanium 6 aluminum 4 vanadium. It's called Ti64, very popular alloy. Then you can see that the K1C values are all very high. very high. That means they're all aerospace alloys, right? So titanium alloy generally will have very high fracture toughness. And what about plane stress fracture toughness testing? So no standard specimens have yet been proposed, and compact tension specimen and other such specimens used for plane strain fracture toughness testing are not suitable. And most investigators use center crack panels, and stable fracture precedes catastrophic failure. A socket changes into a real crack due to stable fracture. Hence, the plane stress specimens need not be pretty crack. Since it is still under the development, and we are not primarily practicing in an engineering setup, I just leave it here, and then I'll move on to our next topic.